Welcome back to Honors Calculus. As the card says behind my head where you can't see it, we'll start into lesson 6 on differentiation rules here with the power rule. Last time, we started looking at how we can find the derivative as a function and then evaluate that function at a point rather than trying to use the limit definition to find the derivative at every point that matters. Here, we're going to start looking at some tools where we can use the various properties we'll be showing, starting with the power rule, to evaluate or to find that derivative function without having to go through and use the lemma definition at all. So let me get my head out of the way, and we'll start off with an idea. I'm going to call it a lemma. I'm not going to prove it. But it is something that you may or may not have seen in the past. It's called Binomial Theorem. It tells us that if we have two real numbers, x and y, and if we have a positive integer, that if we take x plus y and we raise it to the n power, we get this expression that starts off with x to the n plus n times x to the n minus 1 times y plus n times n minus 1 over 2 times x to the n minus 2 y squared. And we can expand out and we get this pattern of coefficients. And it's going to be a symmetrical pattern. So when we get towards the end, we're going to end up with n times x times y to the n minus 1. And our last term is going to be y raised to the n power. Very often, when this is first shown, in an algebra course, you learn about the coefficients in terms of Pascal's triangle. Pascal's triangle starts with the number 1. And then the next row is a 1 and another 1. And for each subsequent row, we're going to have one more term than was in the row before. And the rule is simply the outside terms are 1. And the inside terms, we add the two numbers that are nearest above together. So the first term will be a 1. And then we take these two things and add them together. 1 plus 1 is 2. And the last term is a 1. Then we'll take a 1. 1 plus 2 is 3. 2 plus 1 is also 3. And then at the end is a 1. Then we'll have 1, 4, 6, 4, 1, and maybe 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, and you could keep going. Again, the whole idea of this pattern is for any number, let's say this 20, you take the two numbers that are above it, in this case these two 10s, and add them together, and that's how you find out what's in this cell. But if you take the rows of Pascal's triangle and number them, starting with 0, the entries in the row will give you the coefficients of x plus y to the nth power. So if I have x plus y to the 5th power, that tells me to use this row. And I will have 1 times x to the 5th. Then I'll have 5 times x to the 5 minus 1 is 4, y to the first. I'll have 10 x cubed y squared, right? Just decreasing the power on x, increasing the power on y. I'll have 10 x squared y cubed. I'll have 5x y to the fourth, and I'll have 1 y to the fifth. So not a proof of binomial theorem, but again, it's just multiplying out powers and knowing that this general idea of the power on x will increase the power on y. I'm sorry, the power on x will increase, the power on y will decrease, is really the only thing that is going to matter here. The particular values of the coefficients aren't going to come up in what we are looking at here. The theorem in question tells us let f be a real valued function given by f of x equals x to the n for some positive integer, some natural number, little n. And our claim is that the derivative of this thing is going to be n times x raised to the n minus 1 power. And we will prove this rule using the epsilon delta definition of a derivative. So the derivative of f is the derivative of x to the n, which we can write as the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. And of course, f of x is x to the n. So this is the limit as delta x goes to 0 of x plus delta x to the n minus x to the n all over delta x. And here's where I use binomial theorem. It doesn't really matter what most of the coefficients are. But I know that x plus delta x to the n is going to start x to the n plus n times x to the n minus 1 times delta x. And then there's going to be a bunch of other terms. Each of the other terms, actually, let's throw one more in. It'll be n times n minus 1 over 2 times x to the n minus 2 times delta x squared, and a bunch of other terms. And it's going to end with delta x to the nth power. I'm a little bit low on space here. Nope. Let's try that again. There we go. Let's slide that over a bit so I can finish writing this expression out, because that's just x plus delta x raised to the n power. I still have minus x to the n, And I still have all of this over delta x. Notice here that I have an x to the n and I have a minus x to the n. Those things will cancel each other out, simplifying a little bit so that I have the limit as delta x goes to 0 of n times x to the n minus 1 times delta x plus some coefficient times x to the n minus 2 times delta x squared. I have a whole bunch of other terms here that all have higher powers of delta x, and it ends with delta x to the nth power. And I'm dividing all of that by delta x. From here, notice that every single term in the numerator has at least one factor of delta x in it. And because every single term in the numerator has at least one factor of delta x in it, I can cancel out with that one factor of delta x in the denominator. So I have the limit as delta x goes to 0 of n times x to the n minus 1 plus n times n minus 1 over 2 times x to the n minus 2 times delta x. And I have a bunch of other terms that have a delta x squared and a delta x cubed, all the way up to the last term, which was delta x to the n, and I divided by delta x. So I am left with delta x to the n minus 1 power for that last term. And then here we have some magic occur because I am taking the limit as delta x goes to 0. So that's 0. And all the other terms that have a delta x squared and a delta x cubed and so on are all 0. And delta x to the n minus 1, 0 to any power is 0. The only term that is not 0 is this lead term, n times x to the n minus 1. That's what our theorem told us we would find. We have now found it. We have thus proven our theorem. And so now that we have the theorem, we can use the theorem. If I wanted to take the derivative of x raised to the 7th power, well, this is in the form of x to the n, where n is 7. And if I take the derivative of x to the n, I get n times x to the n minus 1. In this case, that's 7 times x to the 7 minus 1, and 7 minus 1 is 6. 7x to the 6th power. Two quick corollaries. The derivative of x is 1, and the derivative of any constant is 0. And these aren't difficult. They follow exactly the rule that we just talked about, although they are a little bit, I'm not going to say hard, but they're easy to forget that the rule still applies. Because x is the same thing as x to the first. So the derivative of that will be n, which is 1, times x to the n, which is 1 minus 1. So we have 1 times x to the 0 power. And anything to the 0 power is 1. So we have 1 times 1, which is 1. And if we think about the derivative of a constant, well, using exactly that property, anything to the 0 power is 1 backwards, we could write a constant as k times x to the 0 without changing anything at all. And by doing that, we can now have this as k times the derivative of x to the 0, right? You can factor a coefficient out of the derivative. We showed that in the last lesson. And now we'll use the properties of exponents. This will be n, which is 0, times x to the n, which is 0 minus 1. All right. So we have k times 0 times x to the negative 1. And it doesn't matter what that other stuff is because you're multiplying times 0. And when you multiply stuff times 0, you get 0 out. That's one of several ways of showing that the derivative of a constant is 0. But with those features in mind, we can add to it the idea of linearity, and we can take a look at a polynomial function. For example, if f of x is 5x cubed minus 7x squared plus 11x minus 12, well, then the derivative of f will be the derivative of 5x cubed minus 7x squared plus 11x minus 12. And we've seen that the derivative of a sum is the sum of the derivatives. So this is the derivative of 5x cubed plus the derivative of negative 7x squared plus the derivative of 11x plus the derivative of negative 12. And of course, the derivative of a coefficient times a function, constant times a function, is constant times that derivative. So we'll have 5 times the derivative of x cubed minus 7 times the derivative of x squared plus 11 times the derivative of x and minus the derivative of 12. Right? Using the power rule, the derivative of x cubed is 3, right? Take the coefficient, or the exponent of 3, that becomes the coefficient. And you multiply times x to the same power minus 1. Same thing with x squared. It will be, take that power in front, 2 times x to the power minus 1. And we could do the same thing with the last two terms, but we saw that the derivative of x is 1, and the derivative of a constant is 0. So doing some simplifying, 5 times 3 is 15. 3 minus 1 is 2. 7 times 2 is 14. 2 minus 1 is 1. But I don't write a power of 1. X to the first power is just x. Let's use this as simple as possible. 11 times 1 is 11. Subtracting 0 doesn't do anything at all. So now we can take the derivative of a polynomial function without having to employ the epsilon delta definition whatsoever. If that's not a time saver, I don't know what is. Right. Similar problem for you to take a look at. The derivative of 9x to the fourth plus 12x squared minus 7x minus 14. Take a few minutes, see where you can get with this differentiation, and I'll see you in the next video.